Okay, so welcome to everyone to this second day of NorCAS 2020. I hope you had a good day yesterday. Today we will start with the keynote of Tim Constandinou, and then we will, in the same session, continue with the second plenary session. 1:20, it will be a break of 20 minutes, and then we will continue with two parallel sessions from 1:40. So hope everyone will have a good day and participate in our sessions. After the plenary presentation, I will also announce a link for the voting for the Best Paper Award in the chat. So you can then go in and vote for the 3 candidates among the plenary from the plenary sessions. So I think right now, I think the next step is to welcome and introduce our keynote speaker of today, Tim Constandinou, who is a reader at Imperial College. He will talk about the future human, merging minds and machines. Just give you a brief background of Tim. So Dr. Timothy Constandinou, he is a reader in neural microsystems at Imperial College London. He leads the next generation neural interfaces lab at Imperial, and his group creates innovative new technologies to enable communication between the nervous system and electronic devices for research tools and medical devices. He additionally leads the Biosensors and Medical Device Technologies group within the UK Dementia Research Institute, Care Research and Technology Centre. Within the IEEE, he currently serves as the Brain Initiative Steering Committee, IEEE Circuit and Systems Sensory Systems, and IEEE Circuit and Systems Society Biomedical Circuit and Systems Technical Committees, and is Deputy Editor-in-Chief of IEEE Transactions on Biomedical Circuit and Systems for the 2020-21 term. He previously served on several conference committees like TPC, co-chair for Biocast 2011, 12, 18, general chair of BrainCast, NorCAS 2016-18, the IEEE Circuit Systems Society CAS Board of Governors from 2017-19, and also co-chaired the steering group of the Royal Society iHuman Perspective on Neural Interfaces and Ecosystem. So today I think we'll get a really interesting talk about how to merge minds and machines, and also the kind of impact and consequence on us doing circuits design. So welcome very much, Tim. I will now start the video presentation, and we will have a question and answer session after the presentation. So let me just share my screen.
Good afternoon. Firstly, I'd like to thank the organisers for inviting me to give a talk today. I've intentionally planned this to be a bit broader than what we typically do in CAS, bridging into the area of neurotechnology. I hope you find it interesting.
I've called this talk Future Human, Merging Minds and Machines, as I want to assess where are we today with neural interfacing technology, but also where are we heading? What challenges are we going to meet on the way, and what opportunities will arise? I want to separate the fact from the fiction, but also to give you examples of where we are with state of the art. Most importantly, I want you all to know how the circuits and systems community can really contribute to this field. Science fiction is all around us. It's an inspiration to us, but it also warns us of where we may be headed. Some recent examples include, in Matrix, for example, a direct connection into the brain to upload our thoughts, the ability to learn Kung Fu through brain training, in Avatar, the use of a brain scanner for mind control, and many examples in Black Mirror, for example, as to how these technologies may just go a little bit too far. Are these fact or fiction? Then we have the media that very much likes to pick and choose different quotations to place a sci-fi spin on where neural interfaces are today. Here we have an example in The Independent where the headline was Elon Musk unveils brain chip to download memories. And even for Elon Musk in their announcement, this was very speculative. Another example was a BBC News story that implied that brain implants were being routinely used for drug addiction, although this was really reporting on a small-scale trial of deep brain stimulation used in addiction. Forbes recently published this article that partially inspired my title today, The Merging of Human and Machine. And this really reported on two technologies. One was the Neuralink announcement, that's Elon Musk's company, and the second had to do with advances in neuromorphic computing. Then we've got this Wall Street Journal article that reviewed some medical technologies, including a device for epilepsy, the Apple Watch, and a closed-loop insulin pump. And the headline here was "The AI Doctor Will See You Now." And finally, we've got an example from The Verge reporting on a wearable device that Kernel has recently announced as being a tool for neuroscience, yet it was using the phrase hack the human brain. And so with all this spin, the public, and that's anybody that's not directly related with this research, might be led to believe that capabilities are far beyond what's actually possible today. So what are neural interfaces? I would define this as the direct connection of technical components either to the brain or to the nervous system. These can be used to typically restore a lost function. For example, cochlear implants can restore hearing, or devices in the future could even perhaps enhance our functioning. For medical application, this will ultimately impact the quality of life of millions of people. But thinking more broadly, this may impact the way that we interact with the world and with one another. Imagine being able to control an electronic device simply by just thinking about it. Next, we're going to ask, so what do these devices actually look like? When they're placed outside the body, they typically take a wearable form factor. Since these devices ultimately need to interact with our nervous system, they need to be placed close to the region of interest. A headset would be used, for example, if needing to interact with our brain, or if needing to interact with our peripheral nervous system, this could take the form factor of a bracelet or simply electrodes placed on the surface of our skin. When placed inside the body, these are often referred to as implantable devices. These have three common features: a metal package that typically houses the electronics and the battery, a lead, and then an array of electrodes, which makes contact with the target tissue of interest. Here we can see a device that's used in the therapy of symptoms of epilepsy. Here is a spinal cord stimulation device for chronic pain. Here is a brain-machine interface for somebody that's completely locked in, and this is a cochlear implant. Next, we're going to have a look at what are the technologies out there for interfacing with neural tissue. So this graphic here on the left in blue has got all the non-invasive technologies, and on the right has got all the invasive technologies. As you can see in the key on the top, these are classed into two subcategories in terms of recording technologies or stimulating technologies. This means being able to read or write the activity. If we start off with the non-invasive technologies, the first five icons are referring to recording technologies. Now, these use a variety of different techniques to sense activity within the brain or the peripheral nervous system. So, for example, EEG senses the electrical activity by using electrodes in contact with the scalp. MEG senses the very weak magnetic signals that are produced as a consequence of the action potentials in the neurons themselves. fMRI indirectly senses neural activity by sensing changes in the blood oxygenation, which is an indicator of activity. On the second row, we can see this is supposed to say EMG, which is sensing the muscle signals. FES, functional electrical stimulation, is a way of stimulating responses in nerves through skin. And then we have some other brain stimulation techniques such as transcranial direct current stimulation and transcranial magnetic stimulation. And then we have TENS as a way of being able to stimulate nerves externally. If we look at the invasive technologies on the right, most of these are targeting an electrical modality. So they're mostly different form factors of different types of electrodes. So if we start on the top, we have ECOG, which is a grid of electrodes that's placed on the surface of the brain. The next few, cortical implants, neural dust, neural lace, neuropixels, these are all penetrating probes that are inserted within the brain with electrode contacts to sense the field at different points. The icons towards the bottom are all application examples. So these are all examples that use electrodes in different configurations. And the only exception here on the right is the optogenetics. What optogenetics is a technique that uses a combination of gene therapy, first of all, to make cells sensitive to light, together with some light emitter in order to modulate activity. If we compare the different characteristics of wearable and implantable technologies, we can quickly see the different challenges. I just want to highlight a few which are the key drivers in most applications. Firstly, the level of risk must always be assessed with an implantable. Does the potential reward outweigh the potential risk? On the other hand, things like repeatability, signal quality, and compliance are really key challenges with wearable devices. These mean that for many medical applications, wearables just aren't viable options. Whereas for consumer applications, it's the other way around. Any potential risk, as with implantables, can't really be justified. To list a few medical applications. So first of all, for diagnostics, EEG, that's using scalp-based electrodes, or ECOG, that's using electrodes placed on the surface of the brain, or fMRI, are all generally used clinically for assessing brain function, particularly with conditions such as epilepsy or sleep disorders or any brain injury. Then we have a number of wearable assistive devices. So with things like pain relief, for example, during childbirth or for back pain, or rehabilitation, for example, due to stroke. Finally, we've got a number of implantable assistive devices where we have three categories. So on the left, we have what are known as sensory prostheses. So these are devices that provide a sensory input, such as retinal implants for eyesight or cochlear implants for hearing. In the middle, we have deep brain stimulation therapies, referred to as DBS, that are for conditions such as Parkinson's disease, essential tremor, dystonia. And finally, on the right, we have motor prostheses that are sensing neural activity and using this to control something with it. So for example, a prosthetic limb. Next, we're going to look at a few success stories. Firstly, we've got arguably the most successful implantable neural interface out there. That's the cochlear implant. This bypasses the inner ear to interface an external microphone onto the auditory nerve. There is somewhere between 500,000 and 1 million of these in use today. Secondly, we have deep brain stimulation therapy that's helpful in a number of movement disorders, including symptoms of Parkinson's disease, essential tremor, dystonia, for example. This technique has recently also been extended for epilepsy, and there are a couple of 100,000 such devices in use. I want to show a short video here that demonstrates what impact these devices can have.
The probe that is placed into the brain, I understand, comes level with the top of the nose and the ear. And it is connected to a battery in my chest, in my underneath the skin in my chest here. And this is controlled. I can control the amount of the voltage going in. I can control the length of time that the pulse is. and I can identify the number of times per second that it goes in. And I'll turn myself off now. So one of the problems is not only, as you can appreciate, is that you can't do very much for yourself. The whole personal hygiene has to be done by somebody else. But because my concentration now is up to 90% on my tremor and trying to control it, and I'm thinking the word Parkinson's all the time, I'm not terribly, I'm not concentrating on my conversation with you at all. Okay. You can see that it's quite...
If we generalize what's actually inside a typical neural interface, for example, a cochlear or retinal implant, we have some sensor, a processor to trigger and modulate some stimulation. We call such a prosthesis a sensory neural interface. The clinician or healthcare professional would then calibrate or program the device every few weeks or months. Then we can also have devices that sense activity, interpret it, and use it somehow. These are called motor neural interfaces. More broadly, these are often referred to as brain-computer interfaces or brain-machine interfaces. This is defined as a neural interface that senses neural activity, decodes something useful, and uses this for either communication or to control an external device. And there are two categories. So brain-machine interface normally tends to refer to the invasive devices, and brain-computer interfaces referring to the non-invasive devices. As you can see here, there are two examples of an invasive and a non-invasive device. On the left, we can see a trial of the BrainGate program. This is an invasive brain-machine interface that uses an electrode array that's been implanted into the motor cortex portion of the brain. As you can see on top of the head of this lady, there's a connector that actually plugs into the array, and then all the electronics are external that amplify the signal, process it, and drive this keyboard that we see on the display. On the right, we see a brain-computer interface that's developed at EPFL in Switzerland. This is to enable wheelchair control using an EEG type electrode system. What I would call the grand challenges here is first and foremost the information transfer rate, so the useful information that we can decode out of these systems. If we take communication as an example, we typically type at around 40 to 50 words per minute, and we speak somewhere between 100 and 150 words per minute. The BrainGate device that we see here on the left can achieve at best 5 to 10 words per minute, and that's actually considered quite good. On the right, a brain-computer interface, for example, can achieve a much lower rate, perhaps only 5 to 10 letters per minute. A second challenge is about the chronic stability, continuing to work reliably over a long period of time and not requiring continuous retraining. We don't want a half to 1 hour setup time every day just to get our brain-machine interface working. Next, I would like to shift the focus slightly to circuits and systems to see what relevant activity there is in our community relevant to this area. There have in fact been huge contributions in a number of areas these past 2 decades. to instrumentation, hardware for signal processing, and wireless power and data transfer. We've been reducing the noise, reducing the power, improving accuracy, efficiencies throughout, compactness. If we do a simple search on IEEE Explore with the term neural recording, we can see this upward trend. About 10,000 related papers over the past 20 years, mostly of which are CAS related, with about 1,200 this past year alone. A good example of the impact CAS has had to neuroscience tools is the Intan Technologies devices, founded by Reed Harrison from our community to exploit this widely used low noise, low power circuit configuration that's shown here on the bottom right. I would just like to make a comment here that this is probably one of the only schematics I have in the entire talk. Anyway, this device is used by the majority of tool vendors today and is used in thousands of neuroscience labs every day. A more recent example of a circuit and system technology is the NeuroPixels probe. The realization here has been that in order to increase the number of recording sites or channels, we need to be integrating the electrodes together with the recording electronics, and we can do this with CMOS technology. NeuroPixels has been developed at IMEC in Belgium to provide this high-density recording tool for electrophysiology for neuroscientists. This features several thousand recording sites across the surface of the shanks that are implanted into the neural tissue. The idea is that after implantation, the user can decide which electrode sites to observe the best activity from so as to have fewer acquisition channels than sites. The device currently achieves a power efficiency of around 50 microwatts per channel with about 30 channels per square millimeter of silicon. Crucially, this is now commercially available to this community through IMEC. We can see some technical details here on the right. The architecture uses lots of multiplexers and a quite classical instrumentation front end that includes amplifiers, filters, buffers, and a data converter. This is currently the hottest device available to neuroscientists. In terms of implantable technology, I want to next compare where state of the art is in terms of a human BMI, devices that are clinically used, and research tools that have been developed in our community. So on the left, as I showed previously, is the BrainGate device. What has been achieved here is a good information transfer rate of 5 to 10 words per minute, which is useful to people, but the device has remained bulky, mostly external. The main focus of this work has been on the neuroscience, not on the technology. Another challenge has been the frequent need for recalibration. If we next take a look at what active implantable medical device technology is out there, such as deep brain stimulation devices or cochlear implants, this uses established technology in terms of the packaging, the electrode materials, the leads that have been shown to be chronically stable. The form factor has also been translated into research tools that can be used for human neuroscience. The scalability, however, remains a challenge. The number of channels we can interface with have remained a limiting factor here. Thirdly, if we look at research tools such as the NeuroPixel probes I've just spoken about, these have demonstrated excellent manufacturability, low cost, and scalability, but there are still questions as to the long-term stability and deployability within a fully implanted device. So what are the technical challenges in translating technologies that we've developed within the CAS community, for example, to human-grade neural interfaces? First is the trade-off between spatial resolution and level of invasiveness. Generally, the more invasive a device is, the better its resolution, and we want higher resolution. However, non-invasive devices are also highly desirable. The second trade-off is between the size of the device itself and its scalability. By scalability, we mean the number of channels that we're able to interface to. This generally also refers to the effectiveness of the device, what we're able to achieve with the device. There's a hope that more channels will translate to more effective devices. The third challenge is that of power or energy efficiency, as in all electronic systems. The related trade-off is what we would typically encounter in analog design. So power traded off with noise, bandwidth, etc. Over the next few slides, I want to review some of these technical challenges in some more detail. Firstly is that of the trade-off between resolution and level of invasiveness. This can be illustrated here using a typical brain-machine interface application. What we want to observe is the activity within the cortex. That's the outermost layer of the brain. We're going to consider three different electrode types here. EEG, that's the non-invasive electrode on the scalp of the person. ECOG, which is the minimally invasive type, where you have electrodes implanted on the surface of the brain. And the most invasive are the intracortical penetrating microelectrodes. So we can observe here that the less invasive we get, obviously the lower the spatial and temporal resolution, as is listed on the left-hand side here. This is because the invasive electrodes observe the activity of relatively fewer cells, whereas the less invasive we get, the further away we're from the brain. So we're picking up the activity of entire networks, not just a few neurons. So signals are then noisy and the SNR is also degraded. The second challenge is that of scalability. That really refers to the number of channels we're trying to interface with. Generally, more channels is considered a good thing. This can lead to either an improved information transfer rate, but just as importantly, also robustness through having increased redundancy. Firstly, to mention size, both for implantable and wearable devices, the overall size of the electrodes and of the array is really limited by what it is we're trying to interface with. For implantable brain-machine interfaces, there are two approaches to scaling. Firstly, by making the electrode sites each smaller, we can achieve a higher density over a relatively small area. The second approach is to distribute the recording or the interfacing sites across several smaller devices. And this can achieve scalability in the number of channels, but also have a broader coverage area. This has led to the Moore's law of neuroscience that's observed this exponential increase in the number of neurons that can be recorded over time. Although the doubling time has been estimated here to be about 6.5 years, I believe there are really two rates, before and after microtechnology came along, and that currently puts us at a doubling time of around 4 to 5 years. We can see here at the bottom some examples of high density probes. The third challenge is a major one, that's of the integrity of the signal over time. With invasive electrodes, we have the problem of biocompatibility. And that has two aspects. Firstly, that the electrode doesn't harm the tissue, but also that the body doesn't harm our electrodes. And this really leads to degradation over time. For non-invasive electrodes, we have issues with repeatability. Each time you wear the device, it might not be on exactly the same location, and also comfortable electrodes are generally not good ones. The fourth challenge is one that really concerns us, the CAS community, and that's of energy efficiency. The power is generally proportional to the number of channels we have. So if we want more channels, we need more power, or we need to design circuits to consume less. Secondly, we've got the challenge of the energy source itself. If we're using a battery, this has a certain capacity, or a recharge cycle that places more constraints. We can't have a device, for example, that needs recharging every hour. And then if doing wireless power transfer, we need to make sure we can do this efficiently as possible. That's because the key constraint with power is that of safety. Any power we consume is ultimately dissipated as heat, which can harm the tissue. So generally we need to operate within a 1 degree window. We mustn't rise the temperature of the tissue more than 1 degree C. The fifth and final challenge that I'm going to mention today is how do we deal with uncertainty that's in our signals. Firstly, we need to know how to generalize. All our brains are different, and for wearables, each time we put them on, they're placed slightly differently. Then comes the challenge of training or calibration. For somebody that doesn't have a reference point, how do we calibrate? For example, in someone that has locked-in syndrome, we don't have a clear output to train against. Then, as I mentioned it before, these signals change over time. We can see some examples here on the right of how the signal levels change over the period of weeks. And ideally, all this needs to be autonomous and run in the background, as to not burden the user. So far, I've just been talking about all the problems, but with challenges also come opportunities. So these next few slides, I want to identify some of these opportunities and then dig a little deeper to give you some examples. The first opportunity is to address new application spaces outside medical. Examples shown here include monitoring our sleep, meditation, sensing our emotions, and then there are more ambitious targets of virtual or augmented reality, or even human enhancement. The second opportunity is to innovate the device itself. For implantables, we can look at new electrode materials or geometries. Shown here is the Utah electrode array. This is still the only human-approved device for intracortical recording. What we're seeing are new concepts to neural interfaces, being able to have more electrodes applying our electrode array, for example, through a blood vessel, or the idea of neural threads. For wearables, however, we really need to place some effort on making them both comfortable, easy to use, but also reliable. Here are two examples of a new headset designed for gaming, but also an external stimulation therapy for migraine. I've called the next opportunity New Big Ideas because we really need some, mainly to do with the fundamental science. For example, most brain-machine interface efforts sense activity within the motor cortex, and specifically the portion that has to do with our hand or arm movement, and decodes this to create a control signal. However, no matter how many electrodes we place there, the fundamental limit is still the same. We're trying to control a cursor to move left, right, up or down. So the speed will be limited. A new idea that recently emerged was to instead try to interface with a part of the brain that's traditionally associated with speech. And since we're very good at communicating through speech, that can provide us a significantly more effective way of providing control signals to our brain-machine interfaces. And that can lead to increasing that all-important information transfer rate. I'm sure you've all been expecting to hear something on AI. This is, however, a real opportunity. A good example is that of voice recognition. In the past, there was a single computer program that we would have to keep training it with our voice. And even then, we had to always maintain the same tone, the same volume, or it wouldn't work. Then came big data, when everybody's phone became connected to the cloud, and instantly we had this much greater training data set of millions of people all training the system. And then voice recognition became usable. I believe neural interfaces could benefit from exactly the same paradigm. But in order for this to work, we need some form of standardization. For voice, for example, we have a fixed sampling rate. In imaging data, we have a fixed pixel array. We don't have any of this for neural signals. Next, I have a couple of examples that shows what is possible with machine learning. In this example, using fMRI. This is from Jack Gallant's lab at UC Berkeley. The first example shows participants being shown natural scenes and decoding semantics. The final opportunity I want to talk about is that of using platform technologies. Now, this is a slide I've borrowed from Tim Dennison at Oxford. As we know from other industries, platforms are very powerful business models. If we look on the top left here, we have what's known as a product family platform. One example is how Volkswagen and Audi use the same chassis for different cars, and they differentiate by adding different parts to the different models. A second platform model shown on the top right is that of having a broker or intermediary. For example, Uber connects drivers with people that want a taxi, and eBay connects buyers with sellers. So this is very much a service platform model. On the bottom, we've got what's proven to be a very highly effective platform ecosystem model. For example, the Apple App Store. We have a common hardware platform. In this case, it's the iPhone, where different developers can create different apps for this platform. And then the consumers only need to buy one iPhone, and then they can download different apps that repurpose the iPhone for different applications. And so neural interfaces or medical devices in general can vastly benefit from using this model to create hardware once and then reuse it using software updates. So now we've outlined some of the challenges and opportunities, I want to look at what people are doing. In wearable devices, the big innovations are in exploiting new modalities for neural interfaces. One example is that of control labs that have recently been acquired by Facebook. They use electromyography. This uses electrodes in contact with the skin to detect muscle signals. And these muscles are actually being used as biological amplifiers to boost the neural signals themselves. So Control Labs have developed a bracelet-like device that aims to create an augmented reality. For example, you can use this device to type on a keyboard without there actually being a keyboard there. A second example is that of Kernel that uses an optical technique that's known as time domain near infrared spectroscopy. The idea here is to shine light towards the brain, and by detecting the reflected light, we have an indirect measure of how much oxygen is in the blood at that point. And this can give us a good estimate to the underlying neural activity. So a similar method to fMRI. So if we take a look under the bonnet, or in this case, under the helmet, each helmet contains 56 of these nodes, each of which contains a single light emitter and 6 detectors. There's an integrated circuit that controls the pulsing of light and measures the time it takes to receive reflections to each of the 6 detectors. And this is called time of flight. And by repeating this many, many times, we can gather statistics about the light path and improve the spatial resolution whilst we're estimating the blood oxygenation. This device is initially targeted as a scientific tool for neuroscientists or clinicians. Now let's look at some emerging implantable device technologies. One area here is to combine stimulation with recording to close the loop. We can then use this to more precisely dose therapy and reduce side effects. Examples here are devices for chronic pain or epilepsy. A second relatively new direction is that of bioelectronic medicine. The idea here is to extend neural interfaces beyond the brain and central nervous system, and there's an opportunity here to address a whole array of conditions that aren't traditionally associated with the nervous system. This is because all our organs in our body are communicating with our brain, and by intercepting these signals, it's possible to create new therapies. Some examples that are targeted here include a number of inflammatory or autoimmune diseases. A third hot emerging direction is that of brain-machine interfaces. Efforts here are trying to create high-resolution, high-bandwidth devices. Industry have got some quite ambitious visions. One example is that of paradromics that use a bundle of microwires to record from thousands of channels. The ends of these microwires are bonded to an imager-like CMOS integrated circuit. A second example is that of Neuralink, that's Elon Musk's company. This has developed a device that uses these thread-like electrodes that are then implanted using a robot that itself has been inspired by a sewing machine. Next, I want to take a closer look at what Neuralink is actually doing. The vision is to combine human and artificial intelligence, and the effort thus far has been on technology. This all starts from the neural interface itself, these flexible threads. These are then manufactured in a form that can be easily integrated with an electronic module. And here you can see an earlier device that has a USB-C digital interface. This has been validated on a rodent, as you can see here on the left. A newer device, however, is targeting larger animals, ultimately human, and has also integrated wireless capability for providing both power but also data transfer. As you can see on the right, here is an example of how the device has been used to decode where a pig's limbs are in time. Let's now take a look at the integrated circuit itself. What's been publicized is this 1024 channel ASIC that contains an array of pixels. Each pixel is quoted as being able to both record and stimulate, and there's also on-chip spike detection capability. It was also mentioned how 15 different chips across 8 tapeouts have been both designed and tested in just 2 years. I think you'll agree with me that that's quite impressive, and it really demonstrates what industry can do so well. And this brings me to give you a snapshot of a rapidly growing industry for invasive devices, non-invasive devices, and neurally inspired hardware. And this is just a few of all the companies out there. In the final part of this talk, I want to briefly mention where research is going and give a couple of specific examples that my lab's working on. As I already mentioned, there are efforts to exploit new big ideas, for example, the idea of speech or language decoding. There's also this growing community dedicated to bioelectronic medicine that's looking at devices that interface with the peripheral or autonomic nervous system. And there are many labs also looking at different modalities to neural interfacing beyond using just electrodes. There are also quite a few approaches to developing new architectures or system concepts. One example is that of Synchron, shown here on the right, that have developed a neural interface that can be delivered through a blood vessel using a stent. And so the innovation here isn't just about the device, but also about the delivery method. Another new direction is that of distributed devices. What's shown here is a project that I'm working on, creating a completely wireless network of millimeter scale devices. And this is achieving scalability in a very different way to increasing density of a single device. This brings me to an example of a new device we've been working on. The project is called CANDO. The application is for epilepsy, which is a condition that affects roughly 1% of the population. Amongst several symptoms are seizures that are caused by an abnormal oscillation in the nervous system. And this can have a really devastating effect to somebody's quality of life. Fortunately, most cases can be managed with medication, but however, approximately 1 in 4, this is ineffective. The approach that we're taking uses a technique known as optogenetics. This uses a gene therapy to first of all make the neurons light sensitive. This can help target individual cell types when we're trying to stimulate, in addition to improving both the spatial and the temporal resolution. The CANDO project is targeting focal epilepsy that is insensitive to medication, and it has 3 key innovations. Firstly, the fact that we're using the optogenetic stimulation. This provides us the opportunity to be able to stimulate and record at the same time. This also allows us to implement a new type of closed-loop algorithm, working more like a noise-cancelling headphone rather than waiting for a full-blown seizure to develop and then suppress it. And thirdly, this obviously requires a new type of implantable device. So the next few slides, I'm going to focus mainly on the device development, which is my lab's contribution, but I'll give a bit of a broader overview to the project as well. The device itself has been organized in a standard modular fashion to work within a typical surgical workflow. This has a brain implant, a chest implant, and an implantable lead. The electronic architecture, however, is quite different from a standard implantable device. One key difference here is the brain implant itself is active, so the lead needs to be used to communicate both data but also to transmit power. Normally this lead in a typical implantable device connects directly to electrodes. The chest implant itself houses the rechargeable battery, a central processor, and circuits for wireless charging and external communication, in addition to the circuits needed to transmit power and data through the lead. The brain implant is the neural interface itself. This consists of an array of optrodes, that's optical electrodes, that enable the electrical recording, optical stimulation, and supporting circuits. A key subsystem that my lab has been working on has been the integrated circuit for the brain implant. This has evolved through 4 different design cycles spanning some 6 years. You can see here how it's evolved from left to right. A key challenge has been dealing with the many dependencies across different teams across the project. For example, to start off with, it wasn't clear whether the optrodes would be integrated within the CMOS or bonded onto an ASIC. Also, the number of recording and stimulation channels were not known. Also, the way it would be packaged. What you can see on the right is the final 4th generation ASIC. This has been designed to connect to an optrode fork containing 4 shanks. The idea here is to bond the ASIC to the head of the optrode fork. 4 such optrode forks would then be assembled onto a ceramic base plate that would form the brain implant, comprising of a 4x4 array of optrodes. You can see here the current design. A key feature of the ASIC itself, however, was to develop this AC-coupled 4-wire interface for both transmitting power and communicating data so that multiple chips could be connected in parallel. This was a key constraint in the system integration and the assembly. You can see in the top right some photos of the actual device that have been fabricated. As mentioned, CANDO is a hugely interdisciplinary project. This has been a 7-year partnership between Newcastle University, Imperial College London, UCL, and Newcastle NHS Trust. This was funded through the EPSRC, a UK research council, and the Wellcome Trust, a research charity. The project was organised across 3 work packages. Work package 1 was the engineering team, which was what I was part of. This comprised of the integrated circuit design, the embedded system design, the microfabrication, materials, packaging, the benchtop test, and validation. Then we have work package 2, which was the neuroscience team. This focused on developing the new gene therapy required for the optogenetics, all the experimental work, in vivo, in vitro, and also developing the very important closed-loop algorithm. Work package 3 is the medical team, engaging with the patients, the NHS Trust, developing the surgical process, procedure, and coordinating all the documentation required for the regulatory approvals. This brings me to the ecosystem. What I've learned from the CANDO project is that for neural interfaces to make it all the way, it's really essential to address all aspects of this ecosystem. Often we just focus on the science and technology, and we neglect several of these other aspects. Now to the final slide. I hope you all now appreciate that merging minds and machines is both fact and fiction. Although this is possible at a low level, for example sensory or motor interfacing, we're still some way off from mind control. Circuits and systems, however, is a key enabling technology here. The technology, however, is generally ahead of the science, so we need to be providing new tools to enable new scientific discovery. That being said, there are challenges remaining that we need to keep working on as a community. Ultimately, neural interfaces will impact our way of life. There will be medical and non-medical devices, implantables and wearables. The key now, however, is to improve the effectiveness of the link between the mind and the machine. How do we make it faster, more reliable, and usable? Finally, remember, in order to have real impact, it really is essential to consider the entire ecosystem. Thank you.
Okay, thank you very much, Tim. It was a really, really interesting and inspiring talk.